Welcome to our YouTube episode of Gabversity, where facts don't care about your feelings. This is basically all going to be maths, so if you don't like maths, this is going to bore you. Let us begin. What we need to do is we're going to show the radial wave function of hydrogen. For the orbital momentum L is 0 and the energy state N is 2, which is the next level up, or the first excited state. What we want to do is we want to show that it is normalized. So let us do that. What you can see here, ladies and gentlemen, is the radial wave function is R20, and I've already given Electron what these are and what they do and how they work. All right, so R20 equals C0 over 2A outside of R, and this is given to you in the exam, minus R over 2A e to the minus R over 2A. Okay, and I've already gone through what these are and why. So how do we show that this is normalized? Well, first of all, we have to find C0, but we know that it's normalized via this formula, the integral from 0 to infinity of the absolute or the normalized of that function squared multiplied by r squared dr equals 1. In other words, the probability of finding the particle on a given radius with those energy levels is 1. So how do we now do the formula? Well, we're going to square this and multiply by r squared. So that is going to equal C0, which is some constant, over 2a all squared. Okay, we can pull that outside of the integral. And then we have this part here, which is inside from 0 to infinity of 1 minus r over 2a all squared. Okay. And then e to the minus r over a, because if you square that, it's going to be 2r over 2a, and the 2's cancel out. So minus r over a, and then multiplied by r squared dr. All right. And now let's keep simplifying. So we still got C0 over 2a outside all squared. Now inside 0 to infinity, we can simultaneously expand this bracket and multiply it by r squared. So that is going to be, when you expand this, you get 1 minus r over a, because it's 2 by that. And then the 2's cancel out. So 1 minus r over a plus r squared over 4a squared, and then we times that by r squared. So we're going to get r squared, and then minus r over a, that's going to be minus r cubed over a, plus r to the 4 over 4a squared. And all of that is multiplied by e to the minus r over a dr. Now there's a way actually to solve this integral pretty quick. And it's a combination of something I learned and something I've modified myself. Now, excuse me while I fix this pen. It's a bit stuffed up. All right. So what are we saying here? This is what we can do. Let's take a little break from that, and I'll show you this section. How do we integrate this? Well, there's a way to do this really quick. I'll show you. What you do is you have d and you have I. That's derivative, that's integral. And let's pick this one to derive and this one to integrate. Okay, so we're going to put that out here. R squared minus r cubed a, minus r cubed over a, plus r4 over 4a4. And then this one here we're integrating. So we're going to say e to the minus r over a. Okay, so now let's derive this bad boy. So that's going to become 2r minus 3r squared over a, plus the 4 comes down and cancels with this 4, so it's going to be r cubed a4. And now let's derive it again. We're going to get r minus 6r over a plus 3r squared over a4. And then we derive it again. We're going to get 1. Sorry, I made a mistake here. That's a 2. 2r derivative is 2, so that's going to be 0. Sorry about that. So 2r goes to 2, and then here we've got minus 6r over a just becomes minus 6 over a, plus 6r over a to the 4, and then again, that's now goes to 0, and then this here is 6 over a 4. So I've just kept deriving until the next one here is going to be 0. So that's what I've done here. On this side, I'm going to keep integrating, and this becomes pretty easy. This just becomes minus a by this, and then the next one's going to be a squared by that. Next one's minus a cubed by that, and then a4, and then minus a5. And then what we do is I just say each one of those is multiplied by e to the minus r over a. Okay, so I've just integrated these upwards until I reach 0 here. And then what I do is I draw this line diagonal. That, and I say that the answer, first of all, I put a plus here, a minus, plus, minus, and plus. So the answer for the integral is this by this minus whatever this by this is, plus whatever this by this is, minus, plus, and I keep going. And obviously there's a 0 there, so it ends. So that's the whole answer. But what's even more awesome is that the integral is from 0 to infinity. And what that means is that at infinity, this goes to 0, so all those terms cancel out. And at 0, this goes to 1, but anything that has an r in it goes to 0. So the only ones you have to worry about are the ones that don't have an r in it. So that's 2a cubed, so minus 2a cubed, right? And so we'll put that down here, minus 2a cubed. And then the next one's minus 6 over a by a to the 4th, and minus, that becomes plus 6a cubed. And then this one here is that by that, which is minus, sorry, I made a mistake again. Where am I? 6a cubed. And then that is 6 over a5, which becomes, hold on, what have I done wrong? Damn it, I've done something wrong. 4a4, I don't think that's a 4a4. Should be 4a squared. Oh, sick. It is 4a squared. Bloody hell. That's 4a squared. Squared. There we go. Now that's better. All right, so that is minus 6a cubed. Minus 6a cubed. All right, so those go to 0 and we're left with this. But if anyone knows integrals, you know that that was from 0 to infinity, which means that it's minus whatever the 0 term is. Now the 0 term gives us this, but it's minus that, so that becomes a plus. All right, so that's it, plus 2a cubed. That's the answer. So that means that all of this simplifies pretty awesomely down to this, which equals c naught over 2a all squared by 2a cubed, and that equals 1 because we're normalizing it. So that means that c naught squared multiplied by 2a cubed over 4a squared equals 1, because all I did was expand the bottom and put it here, which implies that c naught squared equals, now those cancel out, so you're left with a 2 here, and the a's cancel, you're left with an a there, so that's a over 2, which becomes 2 over a, so therefore c naught equals the square root of 2 over a. All right, now let's see if we are correct. And yes, we are correct. So now we know what c naught is, and now we know the full radial function. Okay, the full radial function is what we started with, and we just replace c naught with it. So it just becomes, so therefore r20 is just going to equal root 2 over 2a root a, okay, 1 minus r over 2a by e to the minus r over 2a. Now, let me just make sure I'm correct. Yep, that's correct. Beautiful. So there it is. We've done it. That's the formula. So now the next thing is, why is the value of finding an electron very small? The chance of finding an electron is really small near the nucleus. Why is that? Because the probability the probability is related to this. The wave function conjugate by the wave by r squared. The probability is proportional to that. And the thing is, as r goes to 0, that implies that p is going to go to 0. So the chance of finding it near the nucleus is close to 0. And mathematics can tell us that without even having to experiment for it, which is pretty awesome. All right, and the next thing we're going to do is construct the wave functions. That's pretty easy. I'm not going to waste your time with that. Let's see what else. I think that's it. Yeah, constructing the wave function is not too hard. Basically, the wave function is the combination of r to 0 and the radial wave function of theta and phi. And we've done this before in other lectures, so I'm not going to go over it again. If you haven't done the other lectures, all of this will seem like gibberish to you. All right, that's about it. Good to see you all.